Hello everyone, welcome to the second video in this series for aircraft electrical and electronics principle. So in this video is basically continuation from the previous video where we discussed some of the fundamentals of DC electrical circuit. So in the previous video, we discussed about some of the basic components like resistance, inductance, capacitance, and some of the basic law, something like Ohm's law. And also we discussed about what is a voltage, current, resistance, and all these things. In today's video, we'll continue our discussion and we will discuss about resistances in series, resistances in parallel, and a combination of both resistances in series as well as in parallel. And we will also discuss the Kirchhoff law. Now, first of all, resistances in series. Resistances are said to be series connected if the same current flows through them. Okay, so these resistances, they are connected in series. Reason being, the same current will flow through them. So let's say current I starts from your source and then at this point it will have no other path, right? All the current will have to flow to resistance R1. Okay. Similarly, after flowing through R1, again, the current has no other path, right? So if, for example, if we had another path here, okay, so some current could either flow in this direction and the remaining would flow through resistance R2. But in this case, we don't have another path. So all the current will have to flow through R2 and the same way through R3, and after flowing through R3, it will return back. Okay, so the same current I flows through all the resistances. Therefore, we can say R1, R2, and R3, they are all connected in series. Now, what we can do is we can combine these three resistances and find its equivalent or total resistance. Okay, RT, and the value of RT or the equivalent resistance, it will be simply R1 plus R2 plus R3. That is the sum of all the resistances connected in series, right? Now, if you had another resistance connected in series, so it would R4, right? And so on. So all the resistances connected in series can be added together and that will give you the total or equivalent resistance. The benefit of doing that is we can replace this entire circuit by its equivalent value, RT, okay, with the same supply voltage, right? Now let's take an example here. So in this example, you have to find the value of current and voltage drop across each resistor, right? Now, even though the current flowing through the conductors or through the resistors will be the same, the voltage across the resistors connected in series will be different. Okay. So we have to calculate both the current as well as the voltages. So first of all, in these kind of numericals, what you would do is you need to identify if your resistances they are connected in series or parallel. So as per our discussion, we can surely say that resistance R1 and R2 they are connected in series because the same current is flowing through both of them. Okay. So we can use the formula which we have discussed. To find the value of current and voltage drop, we first need to calculate the total or equivalent resistance RT. Okay. Although it is not asked directly in the question, but you will have to calculate that first. So that's our circuit. The total resistance will be simply R1 plus R2. Be careful with the units. Both the resistances, they are in ohms. Okay. So we don't need a unit conversion here. But in other numericals, you may need to convert the units. It's simply 6 plus 4, which is your 10 ohms. Now we are given with the supply voltage or uh, I'm calling it as VT here. It's mentioned as VS. Let's change it. That's my supply voltage. It is given 20 volts. So using Ohm's law, we can now calculate the value of current. Okay. So current will be total voltage or the supply voltage divided by total resistance. That is 20 divided by 10, which gives us 2 amperes. So the current flowing in this circuit is 2 ampere. And the same current will flow through both the resistances because they are connected in series. And logically, they don't have any other path. Right? Now again, we can use Ohm's law to calculate the voltage drops V1 and V2. So V1 is your current multiplied by R1, right? So V1 is the voltage drop across R1. It will be current multiplied by R1. Current is 2, R1 is 6, so it gives us 12 volt. So 12 volt is the voltage drop across the first resistor. Similarly, the voltage drop across the second resistor will be the current flowing through the second resistor multiplied by the resistance. Right? So I multiplied by R2, which is simply 2 multiplied by 4 ohms, which gives us 8 volt. Now to verify your answer, so you may need to in your exams or somewhere, you may need to verify whether the voltage drops we have calculated it correctly or not. What we can do is you can add the two voltage drops together. So 12 plus 8, it will give us 20 volts, right? Which is my supply voltage. Okay. So the voltage drop across the resistances connected in series will be equal to your supply voltage. Okay. If you add the voltage drops, it should come out to be equal to your supply voltage. And this is called as, or this will be your Kirchhoff voltage law. We will again discuss it in a short while, but this is the basic concept of Kirchhoff voltage law, or in short, we call it KVL. Okay. Now, resistances connected in parallel. So in case of series resistance or resistances connected in series, the current was same. The current flowing through all the resistances connected in series was the same, but they had different voltage drop. In case of resistances connected in parallel, the current flowing through each resistance connected in parallel will be different, and the voltage or the voltage drop across each resistor, that will be the same. Okay, so just the opposite. Now, how can we identify if the resistances they are connected in parallel? So you have some current I flowing from the source. Okay. At this point, you have two paths. One is in this direction and another one is in this direction. So the supply current I, it will get divided into two parts at this point. Okay, let's say I2 and maybe some I dash current will flow in this direction. Then again, at this point or at this junction, the current has two paths which it can flow in. So again, I dash will get divided between the two paths. So I3 will flow through this then I2 and then I3. Right? So I2 current will flow in this direction, and maybe I double dash current will flow in here. Now finally, I double dash, or you can say I3 current will flow through here. So since different values of current, they are flowing in each of these resistances, we can say they are connected in parallel. Now again, we can find the equivalent or total resistance of, uh, of this circuit. It will be given by this formula here. So it is 1 over RT, or your total resistance, that will be equal to 1 over R1 plus 1 divided by R2 plus 1 divided by R3. Okay. Let's take a numerical based on this. So again, we are given with a circuit here, right? And these resistances, these two resistances, R1 and R2, they are connected in parallel. Okay. Because different current is flowing through both these resistors. And we have to find the value of current and voltage drops across each resistor. Now again, to find the value of current and voltage drop, we first of all need to find the value of equivalent or total resistance. Okay. Oh yes, we can calculate the voltage drop straight away. So the voltage drop across the parallel connected resistors, they are the same. Okay. So V1 and V2 will be the same. And since you have a supply voltage here, this will be equal to your supply voltage, right? So the voltage drop across resistor R1 and R2 will be 2 volts. Okay. Remember, in parallel, currents are different, but the voltage, they are same, right? So you have this single voltage source, Vs, supply voltage, connected across both the resistor. So whatever is your supply voltage, the same will be the voltage drop across R1 and R2. Okay. So one part is solved here straight away. To find the value of current, we need to calculate total or equivalent resistance. Have I not calculated that? Okay, so to find the value of current flowing through each resistor, instead of calculating the equivalent resistance, we can use Ohm's law. Okay, we would calculate the equivalent resistance, but it will be for another purpose, to demonstrate a concept here. So we can use Ohm's law. Okay, so I1 will be V1 or Vs divided by R1, right? So supply voltage is your 2 volts, R1 is your 2 ohms, right? So 2 divided by 2, which is 1 ampere. Similarly, we can again use this formula to calculate I2. So I2 will be your V2 or your supply voltage divided by R2. That is 2 divided by 4, which gives us 0.5 ampere. Now we also need to calculate the total current flowing in the circuit. Although was it asked in the question? No. Although it is not asked, but let's try and calculate the total current flowing in the circuit. Okay. So to find this total current, we need to calculate the total or equivalent resistance, RT. Okay. So let's use the formula which we have seen. So 1 over RT, it will be equal to 1 over R1 plus 1 over R2. Right? So just substitute the value of R1 and R2. So we'll get 1 divided by 2 plus 1 divided by 4, which will be 3 divided by 4. Now, very important here, this value 3 divided by 4 is 1 over RT. It's a very common mistake that students forget to take the reciprocal, right? So always remember, be careful when you are calculating the equivalent resistance for parallel circuit. Okay, so if you take the reciprocal of that, RT or your equivalent resistance will be 4 divided by 3, which comes out to be 1.33 ohms. And now we can again use Ohm's law to calculate the value of total current flowing in the circuit. So total current flowing in the circuit, it will be the supply voltage divided by the total resistance RT. So it will be 2 divided by 1.33, which is 1.5 amperes. Okay. Now the interesting thing here is these were your currents flowing through resistance R1 and R2. So quite similar to what we have done in the previous numerical, if you add them together, you get 1.5 amperes. So this is equal to your supply current. So the current flowing through each of the resistors connected in parallel is equal to your supply voltage. And that is the concept of your KCL or Kirchhoff current law. The sum of currents flowing through each resistors is equal to your supply current. Okay. Now, although we have discussed the two laws, Kirchhoff's laws, but let's define them and let's discuss them separately now. So Kirchhoff law, there are two Kirchhoff laws. The first one is your voltage law and the second one is your current law. So according to Kirchhoff voltage law, KVL, the voltage drops in series circuit will always be equal to the supply voltage or voltage applied. That is the sum of potential difference across the resistors connected in series will be equal to your EMF applied or your supply voltage. Okay, so supply voltage V will be equal to V1 plus V2. Okay, in series circuit, right? Now, the second Kirchhoff law is your current law, Kirchhoff current law, or in short, we call it KCL. So it says the algebraic sum of the current at a junction will always be zero, right? So we have a junction here, A. So it says that the algebraic sum of all the currents flowing at a junction will be zero. Now, this is the algebraic sum. So it is important to note the direction, right? So these I1 and I2, they are flowing into the junction and I3 is flowing out. Okay. So you can say I1 plus I2 will be equal to I3, or you can say um, if you are considering inward direction as positive, okay, then outward direction will be negative, right? So I1 and I2, they are flowing in and I3 is flowing out. Okay. So that way, you can say I1 plus I2 and plus I3 will be 0, right? So I3, whatever the value, magnitude is, it will be negative. Okay. So I3 is a negative value because of the direction, right? So either you can say the sum of current flowing into the junction will be equal to the sum of current flowing out of the same junction. Or you can say the sum of all the currents at the junction will be zero. Algebraic sum. Okay, algebraic sum of all the current at the junction will be zero. That is your Kirchhoff current law. Now, this is the last example here. So, in this last example, as you can see, this is your circuit. And I would say it's a combination of series and parallel circuit. Okay. So this current I is your supply current. It would flow through resistance R1. Okay. Now at this junction A, let's call this A, the supply current I, it will get divided into two parts, R2 and I2 and I3. Okay. They will flow, and at the junction B, they will combine. Okay. So the I current was splitting into two parts, I2 plus I3, and at junction B, they are now combining together. So I can say the current, the same supply current I will flow through R4. Okay. So now if we see what are the resistances through which same current is flowing. So we got R1 and R4, right? Same current I is flowing through them. So they are connected in series. Okay. Now R2 and R3, they are connected in parallel because different current is flowing through them, right? Through R2, I2 is flowing, and through R3, I3 is flowing. Different current. Okay, so this much we have identified. Okay, now there is one more thing, but we'll discuss it while solving. Okay, that will be more clear. So what I will be doing is I will be starting from R2 and R3. I will calculate the equivalent resistance of R2 and R3 first. And then it is the equivalent resistance. So we can replace the resistance, the two resistance by its equivalent value. Okay. And when I draw that, that will make more sense. Okay. So again, in this question, we have to find the supply current, the current flowing through each resistors, and the voltage across each resistor. And also we have to calculate the power dissipated across R3. Okay. So to calculate the supply current, we need to find the equivalent resistance. Okay. So let's discuss it here. So first, I will start from the two parallel connected resistor. So the equivalent resistance, I would say R23. Okay. Combination of R2 and R3, R23. It will be 1 divided by R2 plus 1 divided by R3. So it will be 1 divided by 6. No need for unit conversion. all the resistance, they are in ohms. 1 divided by 6, 1 divided by, okay. So I will get 6 here. You can use your calculator, obviously. Okay. So 1 plus 3. I will get 4 divided by 6. Okay. Now, very important. Remember, it is 1 over R23. So R23, it will be 6 divided by 4. So 3 divided by 2 or 1.5 ohms. Okay, so the equivalent resistance of these two, it's 1.5 ohms. So instead of having two parallel connected resistors, what I can do is I can replace them by its equivalent value R23, which is 1.5 ohms, like that. Okay. Now, if you see the figure or the circuit, we can say that all the resistances, they are now connected in series, isn't it? R1 is connected in series to R23 and R4. So it's to find the equivalent or the total resistance from this circuit, I can simply add all the three resistances together. So 2.5 plus 1.5 plus 4. 4, 5, 6, 7, and 8. So we'll get 8 ohms is the equivalent resistance for the circuit. Now we need to find the supply current I. So we can use Ohm's law. So current is equal to voltage divided by resistance, right? Using Ohm's law. Now voltage, the supply voltage, it is given 200 volts. 200 divided by 8. I will need to use my calculator just to be quick. Divided by 8. That's 25 amperes. Okay, so the current flowing is 25 amperes. Okay. Now let's go back and see. So supply current is 25 amperes. We have calculated that. Part B, current flowing through each resistors. Okay, including the parallel ones. So as we have seen here, current I is flowing through R1, right? So I will call this as I1 will be my supply current, 25 amperes, and the same supply current is flowing through R4. Okay, so the current flowing through resistance 1, R1 is 25, and the same current will flow through R4 also. Okay, but we also need to calculate I2 and I3, that is the current flowing through R2 and R3. Okay, so let's see how we can calculate that. Now, let's see the in the equivalent circuit diagram, the same current I is flowing. 25 amperes. Okay, so we can find the voltage drop. Okay, for the time being, we still need to calculate I2 and I3. Okay, I'll just note it down here. Now let's move on and calculate the voltage drops. So the voltage drop across resistance number 1 or R1 will be I multiplied by R1, which is 25 multiplied by R1 is 2.5. 25 multiplied by 2.5 comes out to be 62.5 volt. Now let's calculate the voltage across resistance R23. Okay, this one. It will be I multiplied by R23. So 25 multiplied by R23 is 1.5. 25 multiplied by 1.5, which is 37.5 volts, and R4, V4, the voltage drop across R4, it will be I multiplied by R4, which is 25 multiplied by 4. 25 multiplied by 4, which is 100. Now, before moving forward, let me just verify the values. So using KVL, I can verify. If I add them together, it should come out to be equal to 200 volts. So 100 plus 37.5 plus 62.5. Yeah, so it's exactly equal to 200 volts. So all these values, they are correct. Okay. Now, again, here also, I have not calculated V2 and V3, which should be equal. So just, so V23 we have calculated. This is the voltage across both the parallel connected resistor, V23. Okay. So the voltage drop across R3 and the voltage drop across R2 will be equal to V23. Okay. So V23, that is 37.5. This will be the voltage drop across R2 and the voltage drop across R3, because in parallel connected resistors, the voltage is the same. Okay. We have calculated the voltage drop across the parallel part. It will be the same as the voltage drop across each resistor. Okay, so we have calculated all the voltages. This is V4. Okay, now we can calculate the value of I1 and I2 using Ohm's law. Okay, we also know the voltage, we know the resistance, so we can calculate the value of current. Okay, so I3, and then here we'll have I2. So let's calculate I3 first. So I3 will be equal to V3 divided by R3. So what is V3? We have calculated. It's 37.5 volt divided by R3 is 2. 37.5 divided by 18.75 amperes. Okay. And similarly, I2 will be V2 divided by R2. V2 is again 37.5. R2 is 6. 6.25 amperes. Okay. So we have now calculated all the values of current and voltages across each resistor. Now in the last part, we have to calculate the power dissipated across R3, this 2 ohm resistor. So you have to calculate the power across this one, R2. So power across R2, we can say it is the voltage drop across R2. So voltage drop across R2 is V2 multiplied by the current. So in the previous video, we have seen this formula. Okay. So V2 is 37.5 multiplied by the current is 6.25. 7.5 multiplied by 6.25. It's 234.4 approximately watts. Okay. So this is the power across R3 and across R2. You have to calculate across R3. Sorry, let's check that again. So V3 will be the same, and the current will be I3. So I3 is not 6.25, it is 18.75. This one. Okay. So 37.5 multiplied by 18.75. 703.13. So it is for me coming out to be 703.13 watts, or 0.7 kilowatts. Right? So there are several questions in the workbook, quite sufficient for you to practice. So please practice all the questions from the workbook. And as mentioned, I have not covered switches, circuit protection devices, and relay. These are three basic topics. So you can read about them. Okay. I've already provided the link for ebook, right? So in the first ebook, you can read about switches. They are like very short paragraph. You just maybe need to understand the working, which probably you would already know how a switch works, how a circuit protection or a circuit breaker works, and how a relay works. Okay. So you can read about them, and that should be, so that is the end of lecture number 1. Okay. So thank you everyone, and see you in the next video.